Hello everyone, thank you for joining the talk. Today I will discuss a research project of Guy Desaulniers, Andrea, Lodi, Louis-Martin Rousseau, and I on increasing reliability of the multi-depot vehicle scheduling problem. We collaborated with Giro, a world leader in the development of optimization-based software for public transportation planning and postal agencies. The dataset we used was provided by Giro and the Société des Transports de Montréal. We use the bus scheduling planning of a 2-month period and the corresponding real-time AVL data for automatic vehicle location. In total, more than 41,000 trips were recorded during that period. Scheduling decision of the operation planning in public transportation can be split in different problems that are usually addressed in a sequential order. The first problem, the timetabling or frequency setting, consists of computing a set of trips for each bus route and their scheduled departure times. The second one is the bus scheduling problem. After solving this problem, the operator knows how many buses are needed to cover all the trips planned. After that, the duty scheduling, the rostering, and the driver assignment problems aim at assigning duties to drivers in order to cover all the scheduled trips. Let's consider a disruption scenario for the vehicle scheduling problem. In this small example, the 5 trips can be covered by 2 vehicle schedules. The cost optimal solution has short buffer times between trip 2 and the trip 3. On a given day, if a disruption occurs during trip 2 run, such that its travel time deviates greatly from the planned duration, then this disruption will impact trip 3 and trip 5. Indeed, the travel time deviation or primary delay, here represented by the red strip, propagates to trip 3 and then to trip 5 because the buffer time does not allow a full recovery. But what if we do not choose the cost optimal solution? And what if we actually pick an alternative solution that has a slightly higher planned cost, but longer buffer times between the trips? If the same disruption occurs during trip 2, we see that because the buffer time between the trip 2 and the trip 4 is longer, the primary delay will be fully recovered. While cost efficiency is of course really important, schedule should also provide high-quality service to passengers. The quality of a public transportation service is closely related to the regularity of the service or reliability. Service unreliability affects the passenger perception of the public transportation negatively. Indeed, Bates and al. Showed that most passengers put more value on the reduction of travel time variability than over the reduction of travel time itself. Thus, to increase the ridership, public transportation agencies put increasing emphasis on improving reliability. The following parts of the presentation include, first, the problem definition of the reliable multi-depot vehicle scheduling problem. Second, the presentation of the algorithmic framework used to solve this problem. Third, a definition of the reliability matrix used to evaluate the vehicle schedules. And finally, some preliminary results. The reliable multi-depot vehicle scheduling problem is formulated as a set partitioning problem with a connection type of graph. In the connection graph, each node is a timetabled trip or a depot. Nodes are connected if it is possible for a bus to perform both trips one after the other, meaning that the buffer time between the trips is greater than the present time between the arrival and the departure terminal, plus the minimum break for drivers. The problem is to find a set of vehicle schedules such that all the trips are covered by exactly one of the vehicle schedules, and the capacity of each depot is preserved. Each vehicle starts and ends at the same depot, and the number of depots is greater or equal to 2. In order to increase the reliability of the schedules, we consider the stochasticity of the travel times, meaning that beforehand, the probability density function of the travel time of each trip is computed. Using the density of the travel time, the secondary delay and the actual departure time can be computed recursively using those equations, where the secondary delay is the actual departure time minus the scheduled departure time, and the actual departure time is either the scheduled departure time, if the previous trip is on time or early, or the actual departure time of the previous trip plus the travel time of the previous trip and the minimum transit time between the trips. To illustrate this, let's take again the example we had at the beginning of the presentation with trips 2, 3, and 5. The actual departure time of the first trip, trip 2, is equal to the scheduled departure, so 8 a.m. If its travel time is 40 minutes, and for simplicity, let's consider there's no minimum transit time. Therefore, the actual departure time of the trip 3 will be greater than its scheduled departure time, because the trip 3 will have to start 10 minutes late at 8:40. The difference between the scheduled departure time and the actual departure time of trip 3, which is 10 minutes, is its secondary delay. So R3 here is equal to 10, sorry. The reliable multi-depot vehicle scheduling problem is formulated as a bi-objective problem. A weighting method is used in order to find a good trade-off between the two objectives. The first one is to minimize the planned cost. Those costs include a fixed cost per vehicle use and a variable cost per waiting minute. The second objective is to minimize the expected secondary delay per passenger. The passenger perspective is considered by weighting the expected secondary delay of each trip by its relative expected ridership when summing over all the trips of a vehicle schedule. Thus, the crowded trips will have more weights in the objective function. A penalty factor, beta, is adjusted when solving the reliable multi-depot vehicle scheduling problem. A larger beta will penalize more the secondary delays. As for the traditional MDVSP, the reliable extension we propose has a huge number of variables. Thus, its linear relaxation is solved by column generation, which has a great advantage of easily allowing the addition of various constraints. To find integral solutions, the column generation is embedded in a branch and bound algorithm. The problem is solved heuristically. We use branching heuristic, namely a diving method. This method fixes a variable at each of the iterations, and therefore it explores only a single branch. Also, in order to kill the height degeneracy related to the set partitioning type of problem, we use permutations. The pricing problem of each depot is a shortest path problem, which is solved by a labeling algorithm. The labels contain, as for the traditional multi-depot vehicle scheduling problem, the preceding label and the accumulated reduced cost. In addition, in the reliable multi-depot extension, we append the cumulative distribution of the real-time departure, capital D, to the labels. In order to measure the reliability of the vehicle schedules, we developed 3 reliability metrics that are oriented towards the passenger perception of the service. The first one is the probability that a passenger boards a delayed trip. Here, we use a delay tolerance, delta max, that is the threshold beyond which a trip is considered late. In our experiments, we set delta max to 2 minutes. As in the objective function, this metric is a weighted sum, where the weight is the relative expected ridership. The second metric is the average secondary delay per passenger. It is the expected secondary delay given that the secondary delay is greater than our threshold delta max. Again, this metric is a weighted sum of the average secondary delay duration for each trip. The third metric is the average number of trips needed to get back on schedule after the first delayed trip. It measures the average number of trips that an initial disruption will affect. We compare the results of the Reliable Multi-Depot Vehicle Scheduling Problem, or RMDVSP, to the traditional MDVSP and the MDVSP with mandatory waiting time after each trip. This is usually the solution used to alleviate the risk of unreliability. Example of mandatory waiting times or buffer times can be a fixed fraction of the trip duration, a fixed minimum waiting time, or one of the percentiles of the primary delay distribution. We use a delay tolerance of 2 minutes. So we solve one real-world instance from Montreal's bus network. This instance has more than 1,000 trips that run between 6 a.m. and 10 p.m. It has 16 bus routes and 2 depots. At the left, you have the results compared based on the first metric, and at the right, the results are compared based on the second metric. The orange dot is the result of the MDVSP without taking into account the reliability. In gray, you have the result of the MDVSP with mandatory waiting time. Each dot is a solution of a different mandatory waiting rule. In blue, you have the results of the reliable extension of the MDVSP, where the penalty factor beta varies between each point. We can observe that it is possible to reduce both metrics considerably at the cost of a small increase of the planned cost of the order of 0.1 to 0.25%. The results of the RMDVSP are promising, as many of the solutions of the MDVSP with additional times are dominated by the ones of the reliable extension of the MDVSP. For the first metric, the probability that a passenger boards a delayed trip drops from about 9% for the traditional MDVSP to less than 3% for the reliable extension. For the second metric, the average secondary delay duration per passenger drops from about 3.5 minutes for the traditional MDVSP to about 2.8 minutes for the reliable extension. The results in terms of the third metric, the average number of trips needed to get back on schedule after a first day trip, are presented below. Here, the average value of the traditional MDVSP is of about 1.6 trips. When we consider the reliability, it drops to about 1.2 trips. The standard deviation decreases as well. For the metric, for this metric, the results of the RMDVSP are comparable to the ones of the mandatory buffer time. The solving time of the RMDVSP takes about 1.5 times the solving time of the traditional MDVSP. In conclusion, we propose a new reliable approach to the multi-depot vehicle scheduling problem that considers the stochasticity of the travel times. Also, we define 3 reliability metrics focused on the passenger. Finally, we presented preliminary results on instances derived from Montreal's bus network. In future work, we would like to compare the reliable multi-depot vehicle scheduling problem on other instances of larger size. So that's it for me. Thank you for your attention, and please do not hesitate to ask your questions in the Q&As or privately using the address below.